Good evening, everyone. My name is Kaylee Zazula, and I am the program manager for Travis Audubon. I appreciate you all being here tonight. We have a really great presentation ahead. Before we get started with our program, I would like to make a couple of announcements. As you may know, our 15th annual Victor Emmanuel Conservation Award celebration is coming up on October 3rd at the Country Club, and we are honoring Virginia Rose, who is a former Travis Audubon board member and the founder of Birdability, a national organization that ensures that birding can be accessible for absolutely everybody. If you would like to join us and purchase a ticket for this event, we do have tickets still on sale. We also have a silent auction associated with this event, and it went live on our website today. I encourage everybody to check out the silent auction. In just a minute, I will put a link to it in the chat box. Additionally, fall migration is underway. We have millions and millions of birds migrating through central Texas as they head south for the winter. And so we encourage everybody to turn out their lights from 11 p.m. to 6 a.m. every night through November 30th to ensure that we cut down on light pollution, which can really mess with birds' navigation because they use the moon and the stars to navigate. So I will also leave a little bit more information about Lights Out Texas in the chat box. So I am going to go ahead and turn it over to our board president, John Bloomfield, who is going to be introducing our speaker this evening.
Hi there, everybody. Thanks for joining. Really excited about tonight's presentation to learn more about raptors from Craig. I think the study of raptors is like the study of all birds is really a lifelong endeavor, and something that's really captivated me since I began birding many years ago in New Jersey. And being from New Jersey, one of the raptor courses I took was with Pete Dunn. And when I am looking for inspiration about birds, I always turn to Pete's writing. And he once described an encounter he had with a peregrine falcon while birding with a man called Harold Axtell, who was the curator of biology at the Buffalo Museum of Science. And Pete asked the question, why do you think people are so captivated by birds of prey? And his friend answered, I think that people are drawn to their fierceness and freedom. These qualities are suppressed in human society, so we project them on the birds. And Pete demurred a little bit, saying, fierceness, he thought, is a human attribute. I don't know if it's applicable in nature. Formidable, yes. Evolutionary, refined, yes. But fierce? But then Harold said it was a projection. As for freedom, as a biologist, Harold knew that birds of prey live lives as hemmed in by necessity as our very own. To our earthbound eyes, a peregrine cleaving a path through the open sky might ignite a sense of freedom in us, but the bird was simply responding to biological necessity, fleeing her Arctic breeding grounds for the shorebird-rich mudflats of eastern Brazil, where she would remain until her biological clock announced that it was time to return to her Arctic nest to pair, breed, and begin the peregrine life cycle anew. And it's kind of fitting that we have a peregrine up on our screen right now. I wanted to talk a little bit about Craig Farquhar, and then I'll turn it over to him for our presentation. He's a conservation biologist, raptor ecologist, and illustrator, formerly with Texas Parks and Wildlife, and currently teaching raptor ecology and the ecology of Rarity at Texas State. He received his PhD in raptor ecology and wildlife biology at Texas A&M, and later became a Frank Chapman postdoctoral fellow in the Department of Ornithology at the American Museum of Natural History in New York, studying the raptors of South America. He, along with co-author Clint Boal, published Raptors of Texas in 2022. So without further ado, I give you Craig Farquhar.
Well, thank you very much. Greetings, everyone. We're all fellow Raptor files, at least bird files to some extent. It's really great to be talking to a group that knows something about these birds already and as inspired by them as I am, and correctly, saying that these birds have been, admired and revered and but also reviled over, millennia, and we can't escape the connection with them. Um, so I want to present, what I'm calling this the Raptor advantage. Uh, if I get this to work here, the Raptor advantage. So what is it that makes these birds stand out? Why are they so special? What makes them do the things they do? And a little bit about why they're so, admirable, formidable, if not fierce, right? So what I've done is I've taken a lot of the material I use in class for my Raptor ecology course, and you'll notice there's some of it's a little bit denser than other parts, but I'm trying to hit all the highlights that I can that sort of clarify what, hopefully in our minds, what it means to be have this kind of advantage. All right, so if starting off, I cover a lot of territory in this class, as one might expect, but one thing I like to do is challenge people to identify and understand what a raptor actually is and where that term comes from. I also enjoy etymology and word origin. So um, if you did an internet search, you typed in raptor, what would you find? Pretty simple question. And you might have guesses already. Maybe you've done this. Okay, so I just did it an hour ago, and every time I do it, it's the same thing. That's what you see. First page. Of course, these are the F-150 Raptor trucks, right? So you do it again, second page, you may get a raptor, and that, something we might consider raptors is the Egyptian vulture, but also you'll get the Fortnite raptor. 15 pages later, if nothing but trucks, you might actually get a raptor, the raptor that, we get the term raptor from, which is a paleontological term, these old reptilian dinosaurs, right? So that's a cultural thing. We kind of have this cultural fascination, and it's changed over the years. Why is everything called raptor now? And I don't know if I have time to get into all that. I actually took a deep dive into all this early on in working on this book that we published. And in the introduction, I was fascinated by where this term raptor comes from. And instead of devoting 15 pages to the introduction, I just pulled all that out and published a whole paper that appeared in Raptor Research a few years ago, and looking strictly at the evolution of this term raptor. Where does it come from? So what is it? All right, so I've got a long spiel I give in my class. I'm just going to spare you all the minute details, but raptor, so okay, raptor is a Latin term. You probably know that. It's come from the Latin verb rapio or rapio, which means literally to seize and grab, snatch, pluck, that sort of thing. Has the noun modifier tor at the end. Okay, so if you're speaking Latin, if you're using Latin terms, all the way up until the early 19th century, this term raptor would not be referring to a bird. All right, that was a later addition. The early connotations, definitions all deal with the actual Proto-Indo-European root, hypothesized root of this term, rap, which H1 rep, which literally means snatch, pluck, okay? So it's a number of things that involve snatching and plucking, including rapist. Rape comes, that rap is the same root, right? So this is where that term originally comes from, and it just stays this way for centuries and centuries. And I did a deep dive into Oxford English Dictionary, try to get a better handle on this. It appears in Middle English in late 1300s, but that's debatable, highly debatable as the origin of its appearance as a synonym for the bird. It's more of in the context of raptorial behavior. In the 1600s, we have a fairly modern, quote unquote, treatment of birds of prey, or birds in general, by Francis Willoughby. Okay, this is the first complete more or less taxonomy, he refers to these birds as rapacious and birds of prey, but raptors does not appear in this tome at all. Okay, he describes them as having crooked beak and talons and things that we generally associate with them. Sort of generally describes them. He does talk about birds of prey. They're the rapacious and carnivorous birds. The gentle and frugivorous birds, which have similar anatomical traits, are the parrots, and other vague traits like generous size and sluggishness, cowardliness, these sort of things, right? So that's where that was in the 1600s. By the 1800s, the term raptor, still as a snatcher of things, was finally incorporated into avian taxonomy in a more modern sense. This is first by Illiger, then by Vigors. The first term was raptatores, the first use, and that was kind of a cumbersome construction in Latin, apparently, and it didn't last long, right? So it later was changed to raptores, and that term raptores served as the order for birds of prey, both diurnal and nocturnal, all the way through the first 3 AOU checklists up until the 4th edition, the Peters edition, 1931, when it was changed to falconiforms, right? And then split out from nocturnal and diurnal birds of prey. So raptores as a term hung on for a long time. So by the time the 4th edition of the AOU checklist had appeared, it had finally become synonymized with the bird that we know today. Okay, this is the way we think about it. So the raptor, the term raptor actually was coined by a poet, a self-described ornithologist poet in England in the early mid 1800s. The first, in a poem, he describes this, and it's fairly interesting how that was described. But that is the actual first appearance of the of the term raptor in English to be synonymous with the actual bird. And this doesn't even occur you don't see this in the Oxford English Dictionary for some reason. All right, so that's where raptor, and that's, again, this is a much abridged version of where that comes from, but that's raptor as a term has been around for hundreds of years. It became more and more popular the last century, 1900s, and of course took off greatly once we get Hollywood involved. We'll see that in a minute. So raptorial, what do these things mean? We know about the eyes, this superior vision, the beaks, sharp curved talons, also very sharp and curved, and just all generated, all basically evolved to grab, tear, prey, right? Behavior, they do what they do, they snatch and pluck, they still do that, and they do it in a bunch of different ways. But a lot of other birds can do the same stuff. I mean, it's not just unique, really, to these birds of prey or raptors. And so then defining the paper I worked on was really just looking at the term, where the term comes from. I didn't want to even touch how we decided that certain groups of birds should be called raptors. That's still an ongoing debate, but there was another paper published after mine a couple of years later by McClure et al. Who get into trying to define that. Still not having a lot of success. So anyway, we've got this idea that there are groups of birds out there that we call raptors. Other raptorial birds can include, of course, the shrikes. They're in passeriforms, pterodactyliforms, the shorebirds, skuas and yagers are definitely raptorial, right? And then we have this interesting order, Caryamiforms. 2 species in this order. They're both in South America. They are you can see by their appearance, ecological equivalents to secretary birds. They're highly predatory, and they have all of the characteristics of birds of prey. They are not currently considered raptors by and large, in widespread terms, but there are some people pushing for it. They're actually genetically fit, and we'll see in a minute where that works, but they genetically are sort of predetermined to be raptors if we're going to look at raptors in a certain light. So they're not raptors now, technically, or at least non-technically. So genetics, we talk about 4 orders, right? Which we have the cathartiforms with the New World vultures, accipitiforms, all the hawks, eagles, kites, etc., osprey. We've got the falconiforms, and then strigiforms, the nocturnal raptors. The 5th might be caryamiforms, right? So and we'll get to that in a minute, looking at the genetics, but I want to also show where this term raptor seems to have taken a big leap. We blame the discovery of this thing, Velociraptor mongoliensis, but it was Hollywood really that helped it along. In the early 90s, 93. I was actually at the museum, the American History Museum, when they were filming this. We had to go around the backside to get to our office. It was a little bit inconvenient, but kind of fun at the same time. You see that this representation of the Velociraptor is typical Hollywood, not at all the size that it probably was. Here's the actual artistic representation of a Velociraptor. Here's the model that was likely used. This is Deinonychus. It's probably what was used for velociraptors. But it is technically a raptor. And why do we say that? Because of this elevated, very large, overgrown nail on the 2nd digit. Okay, it's called an ungual technically. So all of these have that. And that's really what separates these as raptors in paleontologically. Okay, after millions of years of evolution, we've got these adaptations that have set these animals apart. Raptors appeared in the late Triassic. Their main radiation was in the Cretaceous. They're reptilian. I mean, all these birds are descendants of reptiles, so really all reptiles, right? Most of these reptiles were smallish to mid-sized. They were definitely carnivorous and predatory. They all led to modern birds, have relatively big brains, bipedal, which favored the evolution of grasping. Here's the evolution of 3-fingered hands and the swivel joint here in probably Maniraptora in the late Cretaceous, or sorry, late Triassic. So that all takes place, and that enables the grasping, the flying, the flapping. They still retain these talons on the fingertips, which is nice for if you're a predator. But that we see how this eventually evolves to what we have in modern birds, which is mostly just a fused remnant of those 3-fingered hands. They were fast and agile, flight capable. They had feathers, large brains for the size, large eyes and binocular evolution, excellent eyesight. And we say that because reptiles overall and birds have cone systems, right? Photoreceptors, and that enables that alone helps with a tremendous amount of visual acuity. Their eyes were a little bit more binocular focused or oriented. And so that means their common ancestor must have had something similar, right? So it posited that these early raptors had excellent eyesight. Group hunting has also been posited. And then they're distinguished by, again, these huge solitary claws on the 2nd toe, which we call ungual 2. It's these are the bones at the ends of these digits, the extension of the 2nd or 3rd phalanx. You've got this long curved bone, and over that bone grows a sheath of keratin, and that's your talon, right, or your nail. So this modified distal phalanx, that's ungual 2, and they're all unguals, but ungual 2 is the one that's just overgrown, right? And they're numbered this way. In raptors, they mostly have this configuration with the hind toe helix and then numbering inside out. So 1 behind, 2, 3, 4. And then this 2 right here is the ungual 2 that would distinguish this as a raptor. All right, so back to that same drawing, that same illustration. You see they all are represented, fortunately, correctly with a raised ungual 2, and they keep it off the ground because it's huge and it's easier to carry it that way. They don't want to dull it, so it's not going to, they don't want it to drag through the dirt. are used for killing, right? So the largest of the raptors that we know of was this one right here, Utah raptor, paleontologically, the fossil raptor, which is about that size in reference to a human, pretty darn big. And then this is the bone for that ungual, 9 inches long, just the bone, measured in a straight line from end to tip, and then covered with keratin, it would be even bigger, right? So that's a huge slashing ornament and very useful for predation. Now, there is a bird today, and you're probably already thinking of it, that has a very similar, it's not curved like that, but it has a very pronounced, long, saber-like ungual tube, which is used in defense and can kill people. It can kill things. It's a huge bird. You probably thought about it already, right? The cassowary stands over 6 feet tall in some cases, 130 pounds. This is a big animal. And this is what their toes look like. That's the second toe, right? Numbering from the inside out. So this is the ungual. It's just not curved, but it's definitely highly feared and nasty. If you can get eviscerated. There's an account in here. There's a link to this poor fellow that got one of his arteries slashed and he bled out from an attack by a cassowary. So these things, you know, that appendage lives on. Okay, so to the genetics. One of the cool things, you may have seen this if you're interested in the recent revisions in taxonomy. This is what led us to understand that there are 3 orders of diurnal raptors. Okay, these are the terrestrial land birds. And so it turns out that, interestingly, in every major clade of these core land birds, there is an ancestor that was probably raptorial. So if you think about it for a minute, all of these clades, there's this one here, right? This one that gives rise to this one and all these birds, and this one and all these, including passeriforms, which we don't see here. These were all originally evolved as raptors, raptorial. So that physiology, that anatomy, that lifestyle was very successful, obviously, early on, and it led to development of other species. So where are these? These are cathartiforms right there, the New World vultures, 7 species. Accipitriforms, and I have a start as of 2016, that's when the AOU or AOS separated officially out the cathartiforms from accipitriforms. So accipitriforms are all the rest of our diurnal raptors, except for the falconiforms. Strigiforms right there, the owls, that's another base of a clade. And then at the base of this clade are the falconiforms, and right next to them are the caryamiforms. Clearly some raptor flavor going on there. Okay, interesting also genetically is that there is some confirmation that the evolutionary predisposition genetically for various raptorial modifications and evolutionary trends toward predatory behavior, these things, which were gene ontology categories, and these categories all evolved independently in these 3 orders of birds. So they all have high levels of these gene ontologies, and they're very similar. And the thinking was in this paper that they are converging on the traits that are required that help them be better predators. Okay. So the owls, hawks, eagles, etc., and the falcons, all of them have it. Caryamiforms, I don't know if it's on there, but it wouldn't surprise me. Okay, so these birds are doing something special here, hence the raptor advantage. What is the raptor advantage? Now, 10 minutes into the talk, we've got that going. So these are exceptional birds. You recognize that species, I'm sure, right? Everybody shouts it out, Harris hawk. So the things I want to cover that I think sort of encapsulate the main really highly evolved traits are in the skeletal, sensory, digestive, and behavioral systems. Okay, so special cranial anatomy. What do we got here? Designed for tearing, ripping, and seeing. All right, here's a skull, side view of I think this is a red-tailed hawk. It's still got the keratin sheath over the bone, otherwise it'd be white, right? So here's the nares, the nostrils. This is the upper mandible, lower mandible. This is the orbit. You can see how much space it takes up. And then this bony plate here, which we refer to as the scleral ring, you may be familiar with. These are bony plates that are fused together, a round circle, and embedded in the sclera of the eyeball. It's not unique to these birds, but all these birds have it. All these raptors have it. They're basically keeping this huge eyeball from collapsing in on itself, keeping its structure. But it's also found in other birds, some reptiles and fish, not in snakes, but in some teleos fishes as well. It's got also this, what we call a preorbital process or supraorbital ridge, which is an extension of the zygomatic bone, also called zygomatic process. It shades the eyes, protects from damage, but you see there's a big gap, right, between here and the rest of the cranium. There's no bony covering here, so this is a potential source for injury in many cases. All right, so that's what it looks like in the fully feathered bird. Its mean scowling look comes from the supraorbital ridge, right? There's that skull with the sheath removed. See the bone. There's the zygomatic extension, the supraorbital ridge. Cutting edges of the beak and the tip of the beak, they're sharp-ish, but not really designed for biting so much as tearing and pulling. But the supraorbital ridge can be absent in some raptors. It's not in every raptor. It's gone in turkey vultures and New World vultures. It's not there in the osprey, and some kites don't have much of any, right? So it's not everywhere. It just seems to be where it needs to be, apparently. All right, so the feet, the ultimate snatch pluck mechanism. Here, this anisodactyl arrangement with the halix behind, 3 toes in front. This is the situation in all the cathartiforms, excitriforms, and falconiforms, except for the osprey. Osprey is a little bit different. It has a situation that's more like owls. Here's the halix, this would be D1, the digit number 1, and then 2, 3, 4. So this would be the left foot, right? And numbering from inside out. So here's 2, 3, 4. All right, so what this one does is it's able to reverse digit 4 to go backwards and help out digit 1 for grasping. This is called the semizygodactyly, or they're semizygodactyl, so they're facultatively able to move that or abduct that digit number 4. Here's the osprey. You also see here foot pads. In the foot pad, you see these studs, which are another adaptation here for osprey that help it hang on to these slippery fishy prey. So semizygodactyly is also found not just in owls and osprey, but Atlantis kites, it turns out, which have some interesting convergences with owls. They swallow their prey whole. They have similar they have asymmetrical ears. They have very low stomach acid. Some interesting, and they actually have some rough sort of adaptations to the leading primary feathers, which mimics the serration that you see in owls. So they're able to fly more silently. So the gray-headed fish eagle, lesser fish eagle, all these have this semizygodactyly. And of course, it's found in other birds as well. Probably ancestral in passeriforms, turns out. All right, so there's a lot of variation in these feeding apparati. You got black vultures, the lappet-faced, and hook-billed kites here, gyrfalcon, stellar sea eagle, barn owl, all these different. This is, of course, American goshawk now. These things all adapted for various purposes. In the turkey vulture, This is a you know, bird that spends a lot of time on the ground, and its talons are pretty dull. But the secretary bird also spends a lot of time on the ground. Its talons are a little sharper. All responses basically to selection for feeding. All right, for flight, we've got some amazing adaptations. So this is the albatross, right? These are big birds. These big birds have high aspect ratios in their wings. They're long, narrow, and they are pointed, and they don't have much in the way of, or anything in the way of notch primaries. They can't really get off the ground unless they have a wind or some kind of a runway, right? They need some prevailing wind to get off the ground. Whereas raptors can take right off. A bird of roughly the same mass can jump right off the ground and get going, right? So we know this. This is another amazing advancement in flight, largely credited to the shape of the wings and then these notch primaries, which help with lift and thrust mostly. Not unique to raptors, but used to a great advantage, part of their raptor advantage. All right. So this is what some of these notch primaries look like. Golden eagle. This is from this great feather atlas, which you can find online. It's Fish and Wildlife, their forensic feather atlas they use to identify smuggled birds and so forth. So golden eagle, brown pelican, sandhill crane, red-tailed hawks all have, you know, similar shapes in what they do with their primaries. The leading edge is virtually absent, and there's a huge gap, a huge notch down the vein almost to the end, proximal end in pelicans, and pretty severe in golden eagles, red-tailed hawks, really severe in sandhill. So this is this helps with thrust. And how does this work? Well, glad you asked. These are birds that need to take off and move through the air, right? And so movement through the air creates turbulence at the end of the wings and at the tail end of the wings. A lot of stuff going on there physics-wise. This is a jet with a vortex off the wingtip. So one of the solutions there to decrease drag is to use a winglet, an elevated little projected part of the tip of the wing. This helps to bring down some of the turbulence, not make it so rough, right? And not make it so dramatic. That helps a little bit, but birds have a much better idea. That's where the notch primaries come in. So these notch primaries act as little winglets that are able to move and disrupt that intense vortex that comes off the wingtip. And that actual movement, in addition to flapping, helps it move through the air, decreasing turbulence as it goes. So that feather notching is what helps with that. Okay, other aerodynamic processes that they find very helpful is something called the ground effect, right? So you've got air that it takes up only so much space, and so when an object is close to the ground, pushes down the ground, it pushes the air, acts as an air cushion, and so a lot of birds take advantage of that. You see that in raptors as well as, of course, pelicans flying over water. This is some kind of shearwater, maybe audubons, and then great horned owls. A lot of raptors will take off. They don't want to spend a lot of time flying. Flying makes them discoverable, or flapping does, and so they'll take off from a perch, immediately go down low to the ground, and hit that ground cushion, that air cushion that keeps them suspended without having to flap their wings. And then they come up, swoop up, and grab their prey. Okay, this brings us to the thing that most people recognize as the most highly evolved component in raptors, right? Legendary vision. This legendary vision has been the thing of legend, right? So what is it? There's several anatomical and well, mostly anatomical, physiological things that really go a long way to help raptors be better than other birds. Now, other birds have these things. Most of these things we'll talk about here are not unique. They just uniquely evolved. Here's what you could call the raptor advantage in vision. So just we're going to go through these briefly, but sort of in order. Large tubular eyes, which gives more surface area for light to hit. Larger pupils, faster ciliary muscle twitch, which regulates the lens shape. Denser photoreceptors, direct brain connection between the photoreceptors and the brain. 2 fovea per eye, greater magnification, because you have 2 fovea, and the fovea themselves have vitreous fluid, which seems to help magnify incoming light. Increased flicker fusion threshold and highly precise vestibular ocular reflex, which is something we all do every day and probably don't realize it, but this is taken to another level with raptors. Nice black and white hockey there. Okay, so the eyes. What is it about the eyes? These things are known for their extreme abilities to see. They basically compartmentalize their adaptation into 2 broad components, if you will. You know, we talk about, everybody wants to know how much better they are than humans. It's hard to say, really. It's just a wild guess. They're at least 2 times, and you know, probably maybe up to 6 times better, depending on what you mean and how you're measuring that, and depending on what kind of light and so forth that you're in. There's a paper that came out in the 70s, I think, talking about, you know, giving some perspective that we can understand. So American kestrel at the top of a 60-foot tall tree can see apparently a 2-millimeter insect down below. Okay. Red-tailed hawks, other raptors we've seen, you've been in the field, I'm sure you've witnessed a solitary raptor sitting there just minding his business and then takes off and comes back the lizard, and it had come from 100 yards away. I mean, how is it seeing that? The 2 main components here are visual acuity, which all those things that we described a minute ago, except for a couple of them. This is the ability for these eyes to detect spatial detail, and it's a function of their predatory behavior. So raptors, birds that we consider raptors, some of them aren't as visually acute. So carrion eaters, and they just don't need that, right? So they have the lowest visual acuity. Then perch hunters would be next, and then aerial hunters, eagles and falcons for sure, at the highest visual. And we just, you know, we always are in awe of the mighty peregrine. It's the fastest, it's got the best vision, it's just badass, right? So that's where that one fits. They're aerial hunters. Visual acuity is one component. The other is visual perception. This is brain and nervous system. Helps to interpret and to give commands to the rest of the body so that it's able to see these things and do what needs to be done. So those 2 main components. The basic eye anatomy is somewhat similar to other vertebrates, right? They have a cornea, they have a lens, they have 2 foveas. That's just sort of a generalized bird diagram there. So basic anatomy is similar to other vertebrates, it's got some modification. They have the largest eyes, right, in proportion to their bodies of all vertebrates, as you notice from that skull. So they're also proportionally larger than in other birds. Their eyes face forward more so than in other birds. Greatest in owls, of course. And so they really have great use for binocular vision. There's an owl versus pigeon. You can see the overlap there in purple is binocular vision. So a lot of binocular vision is required. So this other organ that shows up in birds, actually in some reptiles, is this thing called a pecten oculi, which you may or may not have heard of. It's just this thing that sticks up right where the optic nerve exits the eye. And it's an organ that seems to be somewhat mysterious. It's not fully known. I think I've read up to 30 functions ascribed to this thing, but mainly the potential functions that it seems to be most reliably associated with by evidence from experimentation is that this is the retina in birds is avascular. There are no blood vessels running through the retina like they do in ours. There is that vascularized choroid layer, which is behind the retina, That's vascularized, but the retina itself is not. So, but the retina still needs nourished, still needs to exchange gases, right? And so this is what this organ likely does in abundance, is to exchange gases. It also seems to have some temperature control, microclimate inside the eye, and some pH control. All right, so the temperature control is likely a function of how much melanin is present. A lot of these pectin are highly pigmented. They're dark, and so they're going to pick up uh, they're going to pick up light and retain it, and it'll be sort of a tiny heater for the inside of the eye. And then this pectin, because it functions as the site for gas exchange and vascularization inside the eye, it frees up space and obstacles. It takes obstacles away from light that would flow through into the retina, increasing visual acuity. All right, highly evolved here. So as I mentioned in that intro, these birds, and like some other reptiles, they have ciliary muscles with greater numbers of mitochondria, which give it a faster response time. They're able to adjust to light much more quickly and change the shape of the lens very quickly. In addition, the iris is similarly involved. The muscles of the iris, though, interestingly, are not just smooth like we have. They also have striated muscle, which may be part of the reason why it's able to contract and dilate much faster. It's innervated by both parasympathetic and sympathetic nerves. As mentioned, these eyes have two fovea, not just one, right? So the two fovea in each eye serve to increase the density of photoreceptors and allow more light to be processed. But you have birds like caracaras and vultures that have only one fovea. Again, these are birds that don't need to be as visually acute. They have solved that by just having the one fovea. There are two fovea. So the two fovea, they have the nasal fovea, which is near the nasal septum. That's the deeper fovea, and it's used for monocular vision, and has the greatest distance acuity. They have different morphologies, which we'll look at in a minute. The temporal is the other lateral out to the side. It's more shallow and used for binocular vision. So something like this. This is a side view and upper view, a little bit of stuff in the way here, but there's a temporal here towards the side, the nasal here toward the nasal septum, right? Binocular, temporal, and monocular nasal. Another look at the eye, just to give an idea what this tubular shape is all about. Here's the scleral plates, and these are swans. This is compressed, anterior-posteriorly compressed eye, actually not round as it is in some other birds of the swan, but see, it still has a pectin. Diurnal raptors are a little bit more extended, more tubular. The owls take it to another level. And notice how, diagrammatically, this is fairly correct. Their scleral plates are extensive. Here's the skull of a great horned owl. Look at those scleral plates. I mean, that just looks like a joke. It looks fake, but it's not. Those tube-shaped scleral rings are embedded in the eye, in the anterior part of the sclera, to keep that eyeball from collapsing. So tubular shape. So the tubular shape allows more light. By the time it gets to the back of the eye, it's spread out more than it would have in a shallower eye. There's greater photoreceptivity. There's greater number of photoreceptors in these fovea. Humans have the one fovea. At 20/20 vision, if we have that, the estimate is like 200,000 photoreceptors per millimeter squared in the fovea. House sparrow doubles that. And in this study, I have this reference somewhere. Buteo, the common buzzard, European buzzard, 1 million photoreceptors per millimeter squared. Okay, there's other estimates that are a little bit lower. This is probably about the highest I've seen, but that is intense. That's a lot of photoreceptors. Okay, in addition to that, that's not enough. Another advantage is that these photoreceptors seem to be connected to as few as one single nerve ganglion per receptor. Humans have about 100 nerves going to each, or receptors going to each ganglion, so much more interference. With raptors, you've got just instantaneous travel, basically, from speed of light. They're myelinated, and so they have great fast impulse transmission from the photoreceptors. Birds have two eyelids. The upper is fairly immobile. The lower one moves to some extent, but and everybody's familiar with the nictitating membrane, which functions kind of like a blinking eye, right, to remove debris and for protection. Okay, here's the fovea. Two fovea in each eye. Upper panels are Harris hawks, lower panels are peregrines, but notice that these are different resolutions. So here's 50 millimeter in this axis, the y-axis is, I think, 250 in that y-axis. So these are different resolutions. So they don't, you would expect the peregrine to be deeper, and it probably is by comparison. There's the deep fovea on the left, and which is the nasal fovea, and the temporal fovea on the right, which is shallower. So this is how this works, right? You've got shallow fovea versus deep fovea. You can have more photoreceptors spread out across this deeper ravine of the deeper fovea, and so the same amount of light hitting the shallow versus the deep will hit more light will hit more photoreceptors in the deep fovea. Nasal and lateral. Okay, so what do they look like? So some of this may be review for some of you if you've had this before. This is a light path going through the anatomy in the retina. And one of the things I like to point out here is that, I don't know if this has been looked at somewhere else. Maybe it has, and maybe somebody has an answer for me. I'd love to know. But if you were designing an efficient retina, would you not put the receptors closest to the incoming path of light? If you're able to make these changes. Instead, you've got all these nerve endings and nerve fibers that run towards the interior of the eye, and then they all travel across as a bunch of fiber patches and exit the eye as the optic nerve. This is some kind of a barrier to light, incoming light. Obviously not enough to make too much of a difference, but it's always been a curious adaptation to me. I don't know, not sure why that is that way. So rods and cones. The rods are, this is kind of what you have almost exclusively in nocturnal birds of prey, in the owls. No color detection. They're extremely sensitive, right? So 1 photon is all you need to fire a rod, but they have slower resolution time. And in diurnal raptors, you have mostly cones in their fovea, 80%, maybe up to 100% in some. They detect color, they have more rapid resolution time, but they need greater illumination. That's why a lot of raptors don't do much first thing in the morning or late at night, because they just don't see that well. They need more light for their activity. Then there's some other, in birds have some other photoreceptive cells, but which is unlike mammals. So it's not unique just to the eye. So what do these cones do, right? So in raptors and other birds and some reptiles, that's why this idea that, the common ancestor must have had these same things, and that might have gone back into early reptile development. So they have these 4 or 5 different cone types with oil droplets, which basically function as spectral filters. And so you've got cones that are designed to or adapted to firing in certain wavelengths. This particular figure shows these peaks, but they could be slightly off depending on the birds you're looking at. But there's basically 4 different kinds here. And then there's a double cone. The double cone doesn't detect color, it detects motion. And it probably functions in magnetic orientation, perhaps, and polarized light sensing. These oil droplets are micro lenses. They help magnify the light and help to distinguish one color spectrum, one part of the color spectrum from another. A focus incoming light, and this is again leading to some people to hypothesize that the common ancestor, even pre-Archaeopteryx, may have been had these and thus excellent vision. The ocular media, which includes the cornea, the anterior chamber with the aqueous humor, the lens, and the anterior chamber, the posterior chamber with the vitreous fluid, those are all fairly transparent and fairly lightweight. And they all seem to be able to absorb the vast majority of the incoming UVB light, which keeps it from hitting the retina. Other birds, not so much. Our eyes, not so much either. But the ocular media is adapted to transmitting very little amount of UV light, mostly in the UVA range, and then maybe only half of that. So this helps to reduce aberration of the images. You don't want ultraviolet light will do that. So that's a problem if you got UV light, and then also just damage the retina. All right, so in terms of, that's kind of the summation of acuity. Perception is another thing. So here we have red-shouldered hawk looking at a prey item down there. This image here may be relevant if you know what I'm talking about. You see a helicopter floating in the sky with the rotors still. This is an optical illusion, obviously. The shutter speed of the camera is about the same as the rotation speed of the rotor, so it looks like they're still. Okay, so this is analogous to what we call a flicker fusion threshold in the central nervous system, the brain. All right, so this is a maximum frequency at which light can flicker before it's perceived as continuous. And so if you're a raptor looking for a mobile prey, you want to determine that it's something compared to the background. You want to be able to see the pattern. If it moves too fast and becomes a blur, then you really can't see the pattern. You don't know what it is. So you've got to have a higher FFT threshold, a higher flicker fusion threshold. Raptors are pretty good at this. But again, it depends on the light. You have to have a good amount of light. They have all this raptor advantage in terms of the anatomy of the eye, right? All this helps to increase the flicker fusion threshold, viewing, distance illumination. There has to be the proper pattern and movement. Humans operate around 50 to 90, which is not bad. You know, anything above that looks like a blur. Raptors take it to another level. Okay, so this is how it's measured. We have a stripe width, various contrasting bands moving in a certain direction, and the number of cycles on and off that are registered in that 1 degree visual field are what determines the flicker rate. So the faster it goes, the more likely it's going to turn into a blur, right? Okay, so this is a couple of examples from looking at water snakes. These are newborn water snakes, and their pattern is plainly visible, right? So if you can see that you're a raptor, you can tell that it's something, probably a search image for it. It's probably something you can attack. If it's moving beyond your flicker fusion threshold, you're not going to see it. It's going to be just a blur. You're not going to know what that is. So it helps to have a higher FFT. Higher in the, like I say, the searchers, the aerial pursuit predators are going to have a higher degree. These are actually kind of low. Chimangu caracara is only in the 15 to 40, less than us. Sacred falcon, 102 cycles per degree. Brown falcons around 73. All these roughly are related to what it does for hunting. Wedge-tailed eagle and peregrine, probably the highest measures so far. All right. One other thing that helps to keep this going for these birds is their ability to keep their head perfectly still while the rest of the body is moving. This is due to what's called the vestibulo-ocular reflex. And this was discovered by a French anatomist who thought this is part of the vestibular system in the inner ear. He thought it was something that had something to do with hearing, so he removed it And the poor pigeon was unable to keep his head up. And so it was then discovered this is not hearing related. It's all about balance, orientation in space. And they also are connected to proprioception in the muscles. So you know, if you're moving, you know which way to move your head. And you're moving your head in the opposite direction of the rest of your body. That is extremely highly evolved in birds of prey. I'm sure you've seen many examples of birds with holding better than this, showing that their head is just perfectly still. If you've watched kites hovering or kestrels hovering, you know, you see their head just stay perfectly still. Their hearing is not that amazing in terms of the frequency range, but there's some cool anatomical considerations here that are worth pointing out. The ear opening in a lot of raptors, just a tiny little hole in the temporal side of the cranium. They're small and they're laterally symmetrical. Owls are much different. Here's a great gray. If you've ever looked at an owl ear, it's kind of amazing. So here's the little tiny owl or a tiny ear hole in a diurnal raptor. Great gray owl, the same great gray owl, this is what this ear is. It looks, if you can stick your thumb in it. It's huge. And not only that, but there are several species of owls and also some hares and kites that have asymmetrical openings. The shape and size and orientation on the skull are asymmetrical, which is another highly evolved advantage if you're need to engage your hearing. So while they don't hear so much high in the frequency range, they really are able to locate where that sound is coming from. Sense of smell, really quickly. The sense of smell is long considered to be the domain of turkey vultures, but this was temporarily cut short thanks to John James Audubon, who provided some kind of weak experimentation, claiming that they don't use their sense of smell, just relying instead on sight, right? So this trend of disbelief actually perpetuated for decades. It was Audubon, for God's sake, so we got to go with them, right? But it was found early in the last century, you may be familiar with this story, that Union Oil Company workers were aware that turkey vultures seemed to be following things and somehow able to locate food by smell, not just sort of, that was just sort of the folklore, right? And so they said, well, let's inject gas lines with something that smells like rotting flesh. And this is mercaptan or ethyl mercaptan or ethane thiol, and it's the same thing. And it was injected in these gas lines, and wherever there were leaks, the turkey vultures found those leaks, and whoa, this is kind of science right there in the field. And so since then, turkey vultures are like, you know, have been the gods of sense of smell in the bird world. Since then, it's been shown that other species probably are as good, if not better in some cases, than turkey vultures. Most birds have a well-developed, it turns out, well-developed olfactory bulbs. And in one study, this study by Cobb in 1968, a long time ago, vultures only had the 8th largest bulbs, olfactory bulbs. So something's going on there. Other birds were studied, and it seems that these all have suggested at least to have a well-developed sense of smell. They have well-developed olfactory bulbs, and they have mitral cells. They have connections between the olfactory receptors and the olfactory nerve, and so all the anatomy is there. And so it's more recent literature searches, literary reviews, and meta-analyses, and so forth have suggested that they have all the anatomical requisites for a sense of smell. And so it's likely that birds in general have a well-developed sense of smell, and certainly for raptors. So there's little empirical justification anymore to suggest otherwise. They may use it for different things. A crested honey buzzard using it for locating food, well known. And then the black kite seems to, and some other members of that clade possibly, are using sense of smell to locate partners. The gastrointestinal tract, more cutting corners here, more efficiency apparatus. They have barbs and spikes going in one direction to keep the food from coming back out. right? These rear-facing barbs, their tongue, surface of the tongue and throat all the way down into the esophagus is covered with keratinized stratified squamous epithelium, and the tips, the little tips there are like papillae facing toward the rear. All of that designed to keep food moving in one direction. So there's the little spike-like rear-facing papillae that are actually keratinized stratified squamous epithelium. It goes all the way down into the esophagus. All right, and so lots of stuff going on with their digestive anatomy, and this is just the surface, but the highlights are, of course, raptors have crops. This helps, but not all raptors have crops. Owls don't. They swallow their food whole, it goes right into the stomach and it's ready for digestion. But other raptors do. Stomach acid is intense, 0.8 to 1 in some species. Bearded vultures, of course, this is like the lammergeier, right, that eats bones. It has intense stomach acid, very low pH. Small intestines and this intestinal tract in general is modified to conserve weight, so it's going to be shorter and smaller. And compared to other birds, Ecdyptiforms are smaller and even smaller still in falconiforms. And the falco, it seems, these are birds for the most part are bird chasers or chasing animals that want to get away. They're very quick and elusive, so that they're sacrificing digestive efficiency for that comes along with having shorter intestines to save weight, to be faster and more agile. But those shorter intestines mean that you've got less opportunity to absorb nutrients. These animals capture regularly high caloric return prey, and just have to keep doing that to feed that shorter and less efficient digestive tract. Okay, the cecum, the paired pouches at the junction between the large and small intestine, they are variable in some raptors. They're longer in owls, but vestigial pretty much in diurnal raptors. So what's going on there? They seem to be, if they're present, they seem to be lymphoid and not glandular, but they can be glandular and secretive or secretory in nocturnal owls. Mostly, in both cases, probably helping with water conservation. So overall, we've skimmed through a lot, but overall there you can separate out these pockets of highly evolved traits into the attackers and the searchers. The attackers' behavioral patterns that require the GI tract to be smaller. They need rapid acceleration, so accipiters and peregrines, you have that sort of really diminished GI tract, and a little bit larger is retained in the searchers, but overall they're still smaller than you see in other birds. Advantages for these guys. Another interesting physiological corner cutting is in what they do for metabolism. I'm sure you're all bird people, that they use primarily fatty acids, fats, for energy sources in flight as opposed to glucose. They still need glucose for general resting metabolism, their central nervous system, vital organs, etc. So they actually maintain a very high circulation of blood glucose, which at that high would probably kill most humans. They rely on the fatty acid metabolism rather than glucose for flight. Compared to mammals, these healthy birds have high insulin resistance. They're not moving glucose into the cells, and they have high blood glucose. And these are concentrations that would indicate hyperglycemia or some kind of blood sugar problem, metabolic syndrome, advanced diabetes in humans, right? But most birds are able to live longer than other vertebrates of similar size, so obviously not impacting their longevity. These high protein diets for raptors are thought to be, or what has led to high insulin resistance and greater blood glucose. So here's a little graph from a nice little study comparing raptors and alligators, which alligators seem to have more of a human demonstration of all this stuff. fasting plasma glucose there on the left, and fasting beta hydroxybutyrate, which is a ketone body from fatty acid metabolism. So this is the level that you would probably want to keep if you're a human, right around 100 milligrams per deciliter in for blood sugar. This is what humans would have, but raptors have it way up here, and they're just fine, not a problem. Okay, pellets. Pellets are used. This is another nice little tidbit from just raptors in general. Not unique to raptors, but generally birds that eat animals that cannot digest everything. So things like feathers, hair, and keratin, insect parts and so forth, bones, cannot be fully digested. These are squished up in as like they're basically like a sponge squishing out all of the liquid digested material into the small intestine, and then it's retained and then moved back out, coughed back out, or egested as a pellet. So there's a difference between hawks and owls. Hawks will egest in the morning, mostly usually every morning, even if they haven't eaten for a few days. Owls will egest throughout the day. So this is, what it might look like. If you're lucky enough, I've never seen this happen. I know it must happen, but I've never seen it. This would be hard to see. You could be lucky. And they're used for prey analysis. So I've used it for my work on white-tailed hawks. It was very useful. Okay, so another cool feature in these birds, how do they cool off? If you're a big black-bodied bird, what do? Well, you dribble your feces down your legs, and it evaporates, and that energy evaporation sequesters heat from your skin and actually helps cool off. This is urohydrosis, evaporative cooling from this urate-rich feces. Cathartiforms in some storks, and they used to be considered to be in the same family. Remember back in the day? This is one of the characteristics that they used to limp them. So functionally similar to sweating. All right. Well, I know we're running pretty quick on time here, so let me try to get through this fairly quickly. You've heard of mimicry in birds, raptors, the classic case with turkey vultures and zone tails, mimicking each other. A lot of studies have been done to kind of verify this. There's still people that are not fully on board, but the zone-tail hawk is the only buteo to exhibit only a dark morph, and the juveniles resemble the adults. So why do they need this? Why do they need just that one morph that looks just like turkey vultures, right? They just, their behavior and their flight pattern and their association with turkey vultures all sort of led this idea that if you have a mimic and you have a model, there must be some mimicry going on. It's not the only example. Everybody, I've never seen one in the wild. I'd love to, but ornate hawk eagle, right? The adult. And then we have this bird. Very similar. Some of you may know what this is. If you have done some birding in the tropics, you may have seen this bird, but this is another bird that's been considered a mimic of the ornate hawk eagle. This is actually a juvenile gray-bellied hawk, Accipiter polygaster. The adult looks very different, but the juvenile, very similar to the ornate hawk eagle. So some mimicry is posited there. Right, so this is originally described as Accipiter pectoralis, the juvenile was, but much later determined to be the juvenile of Accipiter polygaster. So that's how different this juvenile is. Mimicry, possibly, maybe not, who knows. Different foraging styles, whole kinds of ways. Ambush in accipiters, falcons, not so much in caracaras, in the ground, cathartids, accipiters, caracaras, hovering in kites, harriers, osprey, some falcons, the stoop, of course, in falcons and osprey, quartering, harriers and turkey vultures. Mostly all raptors are going to kleptoparasitize within species and between species. It's interesting to watch, and they sometimes will grapple their talons and fall down to the earth in a cartwheel fashion. This is called cartwheeling or talon grappling. It can be injurious if they don't let go. All right, fishing, gleaning in Mississippi kites, swallowtail kites, and a bunch of others. And then the chase we see in falcons, merlins, alpamados, peregrines are all able to have spectacular chases. And of course, soaring in pretty much everything else. And that's it. That's what I've got for you is what I call the Raptor advantage. I hope this has been of interest to you. I may have missed a few things, but if anything else, like clarification on anything, I'd be happy to try to help out. But thanks so much for inviting me.
Yeah, thank you, Craig. It was terrific. We have a few questions in the chat, and I'll go through them quickly. The first one is, many raptors have striking colors to the irises of their eyes. Is there a known reason or benefit to that?
Irises, yes, like we're talking about accipiters and, I'm thinking Eurasian eagle owl and, classic brilliant irises. I am not familiar with any selective advantage to eye color in raptors. There may be some. I'm not sure. The thing about raptors, though, they are, as adults, they're pretty much immune to predation, right? There's not a whole lot of things that prey on them. Smaller raptors are sometimes preyed upon by larger raptors. There may be some freedom there in evolutionary modifications. I don't know. It could be a species selection criterion. I'm not sure. I'm not sure if there's been something overall done for iris color.
Thanks. Another one related to eyes. Do the retinas of harriers have relatively more rods than most of the other diurnal raptors?
That would be a good question. I'd have to plead ignorant on that. I don't know. There must be something in the literature on that out there if there is something. They also use their sense of hearing. So they do hunt, all hours of the day, but they have well-developed ears and asymmetrical ear openings and a facial disc. So they are using their ears as much as they are their eyes, maybe more so in some cases. So I don't know. That's a good question.
Okay. Yeah, next question. Do vultures ever hunt game?
Yes. I mean, hunting, no, I wouldn't say they go after prey as predators like other raptors. I mean, there's the Cara case, which is sort of straddling between predator and scavenger. But some vultures will kill prey if they're not yet dead. If they're, or even if they're, I think there are examples of vultures killing young animals when they're there, but they don't think they go after them as prey items on a regular basis.
Great. And do any birds other than raptors have barbed tongues?
That's a good one. I have to dig back in my general ornithology for that question. I don't know. I'm thinking possibly for birds that eat large prey. I don't know. You stumped me on that one. That would have to be I'd have to look in a general textbook on that.
Yeah.
Good question,
Our folks ask good questions.
Great question, yes.
And one last one from me, since we're at our closing time. If there's one key takeaway message from your talk this evening, what do you most want us to remember?
Well, they're largely all these traits I'm talking about are descended evolutionary modifications from the reptile lineage. So a lot of them aren't new. They're just highly evolved. So in some cases, for example, the F15 threshold, the two fovea, and the number of just the intense amount of photoreceptors packed into those fovea. The fovea themselves, I may have forgotten to mention, the eye is especially uniquely evolved for predation in diurnal raptors. So their vision and their behavioral traits probably are what sets them apart.
Okay. So thank you, Craig. It's been a really informative evening, great presentation, and we thank you for spending part of your evening with us. And thank you to everyone who joined the call, and we'll see you soon. Hope we see many of you at the BCAL.
All right, thanks again.
Y'all have a wonderful evening.
Bye.
Thank you.